And today's seminar is Jeff Harris. Jeff used to work for the Geological Survey of Canada, and now he's a consultant. One of the people he's doing consulting for is the Metal Earth Project, and he's involved with the data integration aspect, and he'll be talking a little bit about machine learning and its application for geological mapping and mineral exploration. So over to you, Jeff.
Thank you. As Richard said, my name is Jeff Harris. I'm working now on a part-time basis with Metal Earth, heading the data analytics section where we're doing a lot of mineral prospectivity mapping in 3D and 2 dimensions. So you'll see me around. I come up usually once a month for a couple hours or a couple days. And I'd like to acknowledge Eric Grunsky, who's also an advisor with Metal Earth, and he hails from the University of Waterloo at this point in time. And Paran Bienya, who is Metal Earth Research Associate, and she'll be actually moving to Sudbury come October, so you'll see her around quite a bit. So that's my way of introductions.
Okay. That's because the mouse is here now.
Okay, great. So remote predictive mapping, when I was at the Geological Survey for the last half of my career, we had the GEM program, which is concerned about mapping the north of 60. And I was heading a project called Remote Predictive Mapping because it's very expensive to go out and map in the north, Canada's north, as you probably all know. And we don't have the people power anymore at the survey to do a lot of mapping. So we developed this remote predictive mapping technique where we encourage the geologists, such as myself, to collect all the available data, geoscience data, be it geophysics, be it remotely sensed, being geochemical, and try to produce some predictive bedrock maps that can be used as a map in its own state, or it can be used to help, more importantly, guide field mapping. So doing this sort of technology, it really depends on the geological environment we're working on. Some environments, say, for example, Victoria Island, which we'll see shortly, are really good for spectral geology, looking at the amount of reflectance from a satellite. Or once we get into more Precambrian terrain, the remote sensing is less useful, and we have to depend on geophysical information, and I'll show you that. The second thing is the geoscience data for mapping. That's going to differ on whether you're in Precambrian terrain, Cordilleran terrain, any type of terrain is going to dictate what is best used for mapping. And those are the 2 themes I'm addressing in this particular talk, is those 2 themes. So the way we can do that is through looking at visual analysis of enhanced imagery. We can enhance it in an image analysis system or GIS system, for example, or we can utilize machine classification algorithms to produce predictive maps. And this is what I'm focusing on today, is the machine application of for geology. The geologic environment, we're going to look at spectral geology, the use of optical remote sensing. Has anybody heard of the Landsat or SPOT or, yeah, so that's what we're talking about in this remote sensing here, is looking at spectral geology, the amount of reflectance, and we'll look at Victoria, the mental inlier for that. We'll look at an example where radar geology works pretty well for superficial mapping in Schultz Lake in Northwest Territories. And then when we get into more difficult environments, like the southern Rae Province, called Precambrian, we'll show you how we use geophysical data, magnetics, gamma ray, and geochemistry. Yeah, you can take that phone now.
That's your phone. But...
Yeah, sorry, I forgot to turn it off. Maybe I should use this for... Just turn it off. So we go into more difficult environments where spectral geology and even radar geology is less likely to work. So I'm going to take you through fairly quickly a lot of these slides. I do have papers on all this here, and if you want papers that describe the details that I'm glossing over, you're more than welcome to hand me your email address and I'll send you the papers. So if you want any of this stuff, just let me know. So the first algorithm we're using, a machine learning language algorithm, is RCM, Robust Classification Method. This is something I programmed, about 15, 20 years ago, and it uses NV software. And it involves putting in your targets or what you want to predict. And in this case, we're looking at superficial materials, water, thin till, thick till, sand, gravel, but it can be bedrock, it can be mineral deposits. And then the second aspect is we don't use all the training areas. We draw training areas for these, but we don't use all the training areas for classification. In machine language, what we like to do is take what's called bootstrapping. We like to use some of our training areas for mapping, for producing the predictive map, and the rest to check it. So they independent check areas, if you like. So that will tell you the percentage, in this case, 20%, we'll use 20% for classification, 80% for validation. Usually I have this set at about 50-50 works well by trial and error. We pick an algorithm, for example, maximum likelihood. And the neat thing is, instead of producing one predictive map, we can produce as many predictive maps as we like. So it's an iterative process, an ensemble processor. And so I'll show you examples of that. And the other algorithm we're using is something called random forest. Has anybody heard of random forest? Or, yeah, I know Richard has. He's done some work with in the Swayze Greenstone Belt, looking at mineral potential. So it's a relatively new algorithm. Well, 2000, Freeman invented it. It requires training data, be them mineral prospects, lithology, superficial, landslides, whatever. And we use this bootstrapping procedure where we only take 2/3 for the classification and 1/3 for validation. Okay, so these are independent. Now, it makes a series of trees, the number of trees defined by the geologist, and each tree, we take our random evidence maps or selection variables, and we put a portion of them down each tree, and it creates a map, a predictive map for each tree. And so what we do in the ensemble approach is we put all those maps together by using a majority classification or the average value, because at each pixel, we're calculating a value. So that's random forest. It's a bit more complicated than that, but suffice for now, it should give you the idea of what we're doing. Okay, let's look at some case studies. Victoria Island, Southern Rae, Schultz Lake, and the Secretary region of Northwest Territories. This is Victoria Island. It was recently mapped by Rod Rainbird from the Geological Survey of Canada. Here we are here, way up in Victoria Island in the Minto Inlier. And here's the Minto Inlier. Notice we have basalts, flood basalts, diabase, carbonates. This is the Minto Inlier through here. So that's the basic geology we're trying to mimic, we're trying to produce. So here's an incredible looking image, Landsat image. How many people looked at Landsat data before? For geological mapping, or what for superficial mapping or superficial mapping? Okay, so this is a 751 color composite of Landsat, and you can see the Minto Inlier here. You can see the brightly reflecting carbonates. You can see the diabase, and you can see the basalts here. So there's so many color differences you can see on this imagery that we already have an idea that this could be useful to map. In fact, Rob, when he was mapping, actually used this data. So that's what it looks like on the remote sense imagery. And here's field shots. This is the carbonates where they weather yellow to red, with the iron in them, of course. You can see the diabase in the background, but you can see that the color differentiation of our different lithological units is quite extreme from a spectral point of view. So that gives us some hope that we can actually do something with this. Here's the diabase, if you like, the cap with basalt, or not the diabase, but basalt, cap with basalts here. Again, you can see some vegetation in green, but it's great exposed ground generally for doing spectral geology. Here, I'm not going to go in detail, but here's the type of imagery we use: Spot 5, Landsat 7, Landsat 8, Aster. Has anybody heard of Aster? No one's heard of Aster. Okay, and then we use airborne magnetics as well. This just tells you the number of wavelengths or bands: near infrared, shortwave infrared, panchromatic, visible. So lots of bands. I'm not going to go through this in detail. What I will mention that's really important is the sun azimuth and elevation. Notice this is 30.4 degrees, 40, 41.9, and then way down to 20.7. So why that is important in doing remote sensing of the north is because if we've got a really low sun angle, like 20 degrees here, we get really poor signal to noise. We don't get a good signal at all. So we don't get good data. Usually we're nominally above 30 degrees, but here our Landsat 7 and Landsat 8 far surpass that. So that's some of the data we're using. One thing we do with remote sensing, and we do it with gamma ray spectrometer, we take ratios of the various wavelength channels. How many people have used gamma ray data before? Yeah. You have to put anyways, we do ratios of the data. For example, the 3/1 ratio highlights ferric iron or Gaussians. So what we're doing here is the third channel in Landsat 7 is the red channel, and channel 1 is the blue. So if we take a ratio between red and blue, then we enhance those ferric iron bearing areas. They're Gaussians. So that's a good way to map Gaussians, if you like. In the 4/3 ratio, we're highlighting vegetation because band 4 is near infrared and band 3 is red. So vegetation, healthy vegetation absorbs red energy, but reflects near infrared energy quite strongly. So that's a good way of helping mask or highlight vegetation. I won't go through all these, but you can see that there's quite a few ratios that can be used to look at various minerals, if they're exposed, of course. And again, getting back to the whole idea of geologic environment. Okay, here's our target that we've already talked about. This is Rob's map. He hadn't finished this area here when we were mapping, but this is what our target, this is what we want to produce. So let's look at the first example, which is only using Landsat 7 and classifying various units here in Landsat 8. Both were above 80%, 89%. When I say 89%, that's classification accuracy. If you compare the mapped units to the independent training areas, which we constructed, then we're getting about an 89% accuracy with Landsat 7 and an 88% accuracy with Landsat 8. So that looks at this RCM classification. So the idea here is I did 20 iterations, and then I took the majority vote, if you like, at each pixel to produce this map, and the same thing for Landsat 8. Now, having said that, because we're working on a pixel basis here in the raster world of GIS, if you like, we can calculate on a pixel basis for our 20 iterations the standard deviation, if you like. And the standard deviation is a measure of uncertainty. The higher the standard deviation, the more uncertain your classification is. And you can see the cool colors here, most of our variation is fairly low in the cool colors. We don't see many reds or oranges, and the same goes for Landsat 8. You see some that has class variability of 3. But this is an uncertainty map that comes as a companion map of the other maps that I showed you. And you can use this uncertainty map in various ways, which I'll show you shortly. This just shows you the classification accuracy compared to when we compare our map to the check areas. And you can see that Landsat 7 and 8 raw data does very well, fairly accurate. And when we add the ratios in with the raw bands here, you can see here, we have good classification accuracy. Now, we don't have good classification accuracy with aster data. You can see it's below 58%, and the TIR, which is thermal infrared, is way down around 38. And that's because of that very low sun angle. The 20.7 degrees is below the threshold of what you really need to do remote sensing in Canada's north. Then we did the same thing with random forest, and this is including all this data: Landsat 7 RON ratios, Landsat 8 RON ratios, ATRA spot, and magnetic data. And this is the result we got from random forest. Now, it turns out that random forest produces a probability map, which shows you, kind of like the standard deviation map, and the probability of the strength of membership of each of these classes. And what I've taken out here is I've only isolated the pixels that has a probability of greater than 75%. So you can see that not all the pixels are classified, but the beauty of this map is that we're more certain of this map because we've taken out the lower probabilities. So this is what random forest can do. And it outperformed, it was about 90-something% when it was compared to our check area. So it outperformed the others. The other thing that random forest is good at is ranking our variables using what's called a Gini index to determine what our most important predictors are. And you can see in this case, Landsat 7 and 8, 5 ferrous iron, these are all common rock forming minerals, span 5 near infrared, and so on. You can see magnetics is down around 20. So again, we can expect all data types to work in all geologic environments. That's very simply said. You have to use common sense. Let's look at southern Rae Province now. Now, this is not a good territory for spectral geology. It's all Precambrian rocks and covered with lichen and forest, etc. We're just north of Manitoba. And this is work that was done by Eric Grumsky, who will be giving a talk shortly, sometime on geochemistry. He's one of the world leaders in interpreting geochemical data. So this is work I did with Eric. So here's the geology map. You can see that mix of tonalites, diorites, granite, gneisses, etc. I will pick out these red areas, which are the much younger Newelton granites. And I'll point them out for a reason, which we'll talk about in a minute. Looking at the Hurwitz sediments, and then these mafic volcanics here. So these are gold occurrences and uranium occurrences here. So this is what the geology looks like. So how well can we do by throwing in various evidence maps like magnetics? This is magnetic, just color shaded. Gamma ray spectrometer. This is what's called a ternary diagram. Does anybody use gamma ray spectrometer? You have an introduction to geophysics, do you not, in this program? Yeah. Yeah. The teacher's probably right here. So maybe we cover gamma ray, but this is a ternary diagram. And that's where we put one color through red. So we put uranium through red, thorium through green, and potassium through blue. And now we can start to see perhaps different phases of the Newelton granite suite. The areas of white is where we're looking at equal amounts, high intensity of uranium, thorium, and potassium emission. Well, there are more daughter elements. Well, we won't get into that. We'll leave that to Richard to explain. But you can see different phases, high in uranium, high in green, which is thorium here. So I think that's representing different phases, because when I worked in Nova Scotia on the Maguma terrain, we had gamma ray data, and we had the same sort of effect here, looking at gamma ray data to map the intrusives. And then we had a whole suite of lake sediment data, very dense data. So we felt we could interpolate that data using something called inverse distance weighted, which is an algorithm for interpolation. So you can obviously see the warmer areas are increased concentration of gold, in lake sediments. We use training strategies. Remember, with machine learning, quite often a lot of the techniques require you to tell them, well, what's the signature for this rock unit? What's the signature for this superficial unit? What's the signature for gold? So we tried training samples where we intersected the lake sediment data with the underlying legacy geology map and used that as a training sample. Or we use legacy field samples and field observations. So you were out in the first year and you mapped and recorded in your computing device what rock unit you're looking at. And the advantage of this method compared to this method is, consider yourself, if you go out in the field for year one and you map, you can take those data, the database you've developed, and bring it home and use ArcGIS or QGIS, whatever you want to use those field samples, which you have tagged with a name, to do the training. So that's a way of building your geological map in the field, if you like. This is all you can do. Here's our targets. In this case, it's bedrock geology, and this is the number of points we had for each training area for this exercise. The first area, okay, is looking at the lake sediment geochemical points. Now you see red and green here. The red is actually what we use to produce the classifications, and the green is what we use to validate or check. Remember this concept of dividing your training areas into classification and validation? That's exactly what we've done here. And again, you can see the rock units plus the number of points used for classification and the number for validation. The second area is, here's the field training points. The same idea goes here. We intersected, we used the database of the field database, extracted the rock unit or lithologic type, and we intersected that to create our RF model. So that's a different way of doing it. I like that way because you're actually building a map on the fly. Here's what the maps look like. This is based on the sediments. This is based on the field stations. And you can see we've done fairly well. I should have had the geology map up here so you can see it, but look how well we've done with the New Elton granite here. They're quite a distinct gamma ray signature, so it's no surprise that works for this type of terrain. And the Hurwitz map pretty well, and some hints of the mafic volcanics are mapped very well. And you can see both methods, training methods, lead to similar results. So that's an actual map you can take out in the field and help guide field work with that. This is the legacy geology that you can compare to the classification, RF classification, using lake sediments and training area. And then, so you can see the interesting part is we've got some same signatures as New Elton granites out through here in the tonalmites and gneisses. It'd be really interesting to go out in the field and check to see, do some field checking to see, yeah, are they New Elton granites? So that's something that we produce using the machine learning. Then what we've done here in uncertainty maps is we've taken out, again, a lot of the uncertainty. The white areas are less certain, so we take those out. So we have a lot of unclassified pixels because they're just too uncertain. Sorry. And then you can produce probability maps of each lithologic type. Again, I draw your attention to the New Elton granites and new signatures out here. Interesting. I mean, it could just be till, but the way they look, it looks kind of like it's bedrock related. And our where's our mafic? Yeah, here, some mafic volcanics. So we can produce a map of each prediction for each. And then what we can do is, remember with RF, you can do the variable of importance. Again, If we only use the geochemical data, we get a 25.6% accuracy when we compare it to our validation areas. If we use the gamma and mag, we get 58.6. If we use everything, we get 77.2%, which is starting to be acceptable. And here's just our major predictors, if you like, from our evidence maps. So for lake sediments, we've got mag as this very strong predictor. The thorium over potassium ratio, thorium, calcium, etc. You can see that. Most of these here, with the exception of thorium, are rock-forming minerals. Okay, so thorium is more accessory type mineral. So you can see how accurate we are getting. All right, so let's move to another environment now. This is in Schultz Lake, where we're looking at classification of Landsat, but particular radar data. And this is work I did with Eric Grunstein and Isabel Martin when I was at this survey many years ago. So what we're seeing now is a color composite, again, a ternary diagram, in which we put two SWIR channels from Landsat 7 through red and green, and the blue channel through blue. And you can see all sorts of stuff. You can start to see vegetation is green, boulder fields, if you like, outcrop, obviously water, and you can see sediment-laden water here too. So there's a lot you can see in this image. It's quite striking. So Eric came up with this idea of multi-beam radar capture. How many people have heard of RadarSat? Anybody ever used any RadarSat data? No. Okay. So RadarSat, you can collect data in various what they call beam modes. So you can collect data where your instance angle is very shallow, or you can look much more steeply at the terrain, or when you're ascending, you're right looking, so you're looking at the terrain this way, and descending, you're looking at the terrain the other way. So Eric figured that this would be a good way to look at the imagery. So it looks like this. You can see this is the imagery for Schultz Lake. This is Schultz Lake right here. And you can see this is S1 ascending mode, S1 descending mode. So S1 is very steep, looking at very steep. And you can start to notice differences as a function of what direction you're looking at in this imagery. You can definitely see the topography here quite nicely. Whereas the much more shallow instance angles look something like this. And they say this is better for surface roughness. Radar is very good at separating topographic patterns, high backscatter from slopes. It's sensitive to the surface roughness and dielectric properties of the Earth. So we get quite different looking imagery. So Eric said, well, Eric's big on principal components. So he said, let's do a principal component of those four images that I just showed you. And this is the image we get. Principal component is a way of reducing variance of a multivariate data set. Does everybody ever use principal components? Or? Yeah, you have, so you no need to explain it to you. Anyways, this is where we put component 1, 2, and 3 through red, green, and blue, and we can start to see all sorts of separation here. You know, with thicker till in here, boulder field, outcrop up here. So that's a striking image for a quaternary geologist to interpret. But we wanted to try machine language interpretation. So what we did is we defined these training areas in ArcGIS or image analysis and QQGIS, whatever. And these were our targets. So these training areas we drew are actually our targets. For example, you can see water here and here and here. So we physically drew these. Now, who drew them? Well, it was actually Isabel. She was our official geology expert. So she figured from her map and what she'd seen in the field, these are pretty representative training areas of these units here. So here's an example of random forest using Landsat, DM, and the 4 radar images versus a traditional quaternary geology map, which was done by field work and by looking at air photos as well. But you can see we've done pretty well with the thick till. Although there are some differences. We've got more extensive sand here. We've got outcrop that we can see matches pretty well. So this, again, you could use that, number one, as first order geologic information. If you're never going to go to the area, you'll never map to the area. It also can be used to take out the field and help you guide field work. How am I doing with the time? Yeah.
You've been talking for 20 seconds.
Okay, good. I'm on track. So now we're going to go to a completely different environment. We're going to do a Cordilleran environment way up here. And this is work I've done with Ken Ford, who's since retired from the survey, and Brian Charbonneau, who is since retired. So all these retired people. I said retired, not retarded. So here's what the geology looks like. Two major blocks, Cretaceous plutons, siltstone sandstones, siltstone sandstones here and up here, more massive rocks up here, and limestone and dolostone here. And this is what the total count looks like on the gamma ray data. And you can see that, geez, we're looking at these are very low gamma ray, punctuated by probably black shales here. And look at the detail we can get here. Whereas this terrain, which is completely separate, these are the dolstones and the sandstones. These are more massive rocks, and these are more shales, sandstones, and siltstones. And you can see the plunging fold here quite nicely here that has already been mapped, of course. So you can see there's a lot of information in this gamma ray data for this terrain. And again, here's a ternary map, except we've used subtracted primary colors here, yellow, cyan, and magenta. And we put thorium through yellow, uranium through cyan, and potassium through K. And you can see some pretty vivid distinctions quite nicely here. More information here in the sandstones and siltstones. Massive is quite different than here. And you can see the Cretaceous plutons. The Mactung deposit is here, and it has kind of a different purplish signature. And that's a tin mine. So looking as type granites in that case. Just looking at the uranium, the amount of detail you can see there, and the uranium-thorium ratio, which is highlighted the Mactung deposit here. So again, uranium, thorium, potassium, we have separate images for each, and we can combine them in a ternary sense. What happens if we look at our field points when we're out in the field, and we said, well, what's the variation of different lithologies in our gamma ray data that we look at that was collected with an airborne sensor, and what happens if we take our ground spectrometer out in the field and try to measure different rockiness, different lithologies, and see what the correlation is. So you can see that here, the ground data at field points, the airborne data where we just marked at the same field points, 79% correlation, uranium, 73, and thorium, highly correlated because Mars responding to accessory minerals is 96. And here are these Fox and Richter plots where this axis just reference response. And the only reason I use these is to show you that the gamma ray has quite different signatures for these various rock units here. You can see that quite clearly in the Fox and Richter plots. So that's a good thing. In fact, what we do with the ground spectrometer is we measure different units and create standards for different types of rock types, and then we use that to compare to the airborne data. Here's some classified maps. These are the raw and ratio gamma data, just the gamma data. And we're using our training areas generalized from the geological map. So we actually drew training areas. Here we took our training areas as our field points here, and tried to look at 89 versus 90% accuracy when we compare it to our check areas. So I hope we can convince you, at least in this geologic terrain, the gamma ray data becomes very, very easy. I think this is gamma and magnetics now. I added the magnetics, and it was even higher. It was about 94% accuracy. And this is something different, completely different. This is where the thing with machine learning languages is you always have to have training data for most of our algorithms, right? You have to tell this is what gold looks like in various predictor maps. This is what this lithology A looks like. This lithology B. But in this case, we didn't worry about any of that. We didn't use training data. We used what's called k-means unsupervised classification. And that did a pretty nice job of bringing out different radio element units. Now, I hesitate to call these geological units at this point in time. They're really radio element units. And we, as geologists, have to go and figure out, well, what is this? Is this, yes, this, I know this is a Cretaceous Pluton. You know, what are these blue areas in here? So we've got a little homework, but just this is just telling the computer, find light clusters in my n-dimensional data, if you like. And okay, I'm getting near the end. Let's look about a different example of mineral prospectivity mapping, or MPM. This is what we're doing in the data analytics section of Metal Earth. We're producing a lot of mineral prospectivity maps of our various transects in both 2 dimensions and 3 dimensions. We're using whatever geophysics we have, 3D geophysics, seismics, geochemistry, and geology information. So this is some work I did some time ago. And again, what is a mineral potential map, or a mineral prospectivity map, or a mineral favorability map? All the same thing. It's just a map that shows potential measured on an objective or subjective scale of a given mineral commodity over a given geographic area using a variety of georeference geoscience data. You know me, I always look at including measures of uncertainty, because even when we map in the field, you know, dash contact is uncertain. You know, the same sort of concept here in machine language, but it's easier to do because we have raster images and we've got to evaluate every single pixel. So it's easy to calculate, as I showed you. So we're going to this area here, which is the same area I just showed you a minute ago, where I worked in the Mountain Granites with Eric. So we're going to use the same area. And the method in the madness, if you like, is we start with a target. What are we looking for? Mesothermal gold, probably not called mesothermal now, it's called orogenic gold, VMS, you know, SEDEX, you know, whatever we're looking at. And from that, we pull out evidence maps or vectors to mineralization, right? And they can be in various formats, binary, multi-class, continuous, a lot of papers on studying which works better. The choice of modeling method, well, I'm using our random forest, and we've had a brief introduction to that. And then random forest actually assigns the weights. And then we come up with a prospectivity map. And of course, we want to see how well we've done. And I'll show you examples of that, an example in a minute. So this is in this work I did with a graduate student of mine. He used airborne magnetics, gamma ray spectrometer, lake sediment geochemical data, and our training was the known gold occurrences. And with random forest, it has to have non-occurrences or non-mineralized occurrences. And actually, you have to have a population of the known gold and a population of unknown or non-mineralized areas. And this becomes a bit of a problem. There's lots of interest in the literature as to what best method is. We use just a random selection of points. And then we use random form to produce. That just reminds you of the geology. We've already gone through that. Precambrian terrain covered. So here's a list of our vectors to mineralization or our evidence maps. I won't go through the fuzzy stuff. We haven't have time for that. But geochemistry, geology, faults, geology. This is what we fed into the random forest algorithms. And this is the result we got. So the binary map, and you can see all the gold deposits fall within the binary map. This is favorable. The darker is unfavorable. So you can see we've done a good prediction of the known occurrences, but we're also getting areas that is telling us that maybe these are more prospective areas. They have the same sort of signature based on the data you put into the algorithm. And here's the probability map. This is what I usually use for mineral prospectivity, because this is the probability map. So the red areas are more stronger, those more stronger related to gold, if you like. So we've got our matrix here, we've got Welton here, not so much, but mostly in our sediments. In our sediments, we come up quite nicely. So that's now, how do we validate this? Well, if we plot areas 0 to 100%, where this is high potential going down to low potential, and the number of gold occurrences we predict in terms of percent, you can see in our random forest model, if we take all, we can exclude this one for a minute. This is an outlier. But if we look at this, we're predicting 80% of the occurrences in about, say, 90% of the area, the high potential area. Whereas this model was a knowledge-driven model that I'm not going to speak about, but it obviously did much poorer, only 55% or so at 90%. So that's one way of validating. There's another ways using rock curves. Has anybody heard of rock curves? I don't see yet. Okay, good. Some of you will know what I'm talking about. My last example, and this is some landslide susceptibility mapping. And this is put together by my colleague Corinne Bienia and Andrea Blaise Stevens, who still works at the GSC. We're looking at Cordilleran, right? So this is the main area. And then this sub-area here is where we've actually done the prediction. So the target here with random forest is where we have more prospective or potential zones for earthquakes, or not earthquakes, but landslides to occur. So we've looked at lithology today, we've looked at superficial geology, we've looked at mineral deposits, i.e. gold, and now we're looking at landslides as another example of machine learning. So this lists the classifiers that they use: 83 degree flow, 181 active layer detachment slides, and 104 rock slides. This is the evidence maps, or the vectors towards landslides for each model. And they were calculated mostly from a DEM, in this particular type, a geology map, and vegetation distribution looking at Landsat. Here again, we're mostly calculated from a DEM, and here a DEM again. So the DEM was dominant in this classification, as you might expect for when we're trying to produce a map of potential for landslides. And here's examples of the three types of flows we just talked about. And you can see the red areas in these are more prone, have higher potential for a landslide based on the evidence we put in. And you can see the landslide and the scars here. So we predicted these pretty well here. These are known landslides here. So you can see that's useful for hazards analysis. I've done the same analysis, mind you, in 3D with land earthquake data. So you can see there's a room for doing this sort of work with landslides, etc. So summary, I think machine classification can play a role in bedrock mapping. It's highly governed by what geologic terrain you're in and what data you have available. And you can usually use it, generally what I use it for was a guide for field work. But in areas, as I said, that we can't map and it's just too expensive, where you just don't have the people. We can use the as a standalone map, but we have to accept the uncertainty in the process. Now, it looks things. The neat thing about geology is looking at geology remotely. You can see things in the data like the geophysics, geochemistry, remote sense data that you can't see on the ground, and vice versa. So it's a really good. This technology is a really good complement towards us helping map in the field or helping our studies. I like random forest because it's got built-in cross-validation. It ranks the importance of the evidence maps of variables. It gives us a measure of uncertainty in the probability maps. And because of its random nature, and I won't go into the details, it prevents or it reduces overfitting, which can be a problem in machine learning. So the geologist, you have a choice. You can classify all the pixels with greater uncertainty, and you can classify fewer pixels, as I showed you in some of these slides. With you can take out the uncertainty, but you have fewer pixels classified. So fast and furious. That's all I have to say. There's a lot of details I've skipped over, but as I said, in Metal Earth now, we're doing a lot of this prospectivity mapping. So if you have an interest in that, you can talk to myself, or Richard's done some great work with a graduate student on this sort of work in the Swayze Greenstone Belt. So Richard's really quite cognizant of this technology and where it's going. So I have copies of the paper here. I can, if you got an external drive, I can give you now. Or if you write your name on a paper, I can send you the papers that will describe this in more detail. Okay.
Good, thank you. Jeff, that's good. Do we have any questions?
Oh, you didn't understand the thing I was saying, right?
Oh,
Yeah.
Sarah.
Yeah, something based on some of the initial slides you showed, I think on the Landsat images.
Yeah.
Where you were showing a summary slide of the table of classification.
Yeah.
Could you pull up that slide a bit, please?
Sure. Hey, you tell me when. Was it Victoria?
Towards the front of your presentation.
That? No?
No, no, yeah, go earlier, I think. See. Yeah,
Right there?
Right there.
Yeah.
So, if I understand, so you have derived formulations of ratios of different.
Yeah, those were taken right from the literature, and because Aster has more visible and shortwave infrared and thermal bands than Landsat 7 or 8, there's more channels. Now these channels actually represent different wavelengths. Okay, obviously wavelengths. I just put the channel number in there. So even channel 5 in Landsat 8 is not the same. Is the same as channel 4 in Landsat 7. So I just put that for ease of presentation.
So do this correlation with particular bedrock features translate across, like stay consistent with the ratio of the particular wavelengths channel is associated with?
Yeah.
Across different study areas, like what you
they're not what they'll get at. Let's say if you do a 3:1 ratio, what it will tell you is these are red rocks, gaussons that are quite red. So it won't tell you the amount of iron in it unless you're using hyperspectral. Has anybody heard of hyperspectral data? It's where you have many wavelengths. And now you can actually identify minerals. So you could tell whether it was jarosite, goethite, or whatever you have, but you have to have the data to do it. That's why I said in the two most important things are geologic environment and the data you have. I've done a paper on Gaussians where I've used Worldview 3, and it's got lots of channels in the SWIR, which is really good for mapping different types of alterations. So it depends on the sensor, yeah. But it's standardized. Just because you get a ratio value of, say, 2.5 in one area does not mean it's equivalent to 2.5 in the other area. It's scene dependent. It's scene dependent. Yeah. Okay.
So
that makes sense.
What will work in, say, Western Canada may not work in Northern Manitoba.
That's right. And that's what I'm trying to say in this whole presentation. Yeah, machine language is great. Number one, it never will replace field mapping. We always have to map and see the rocks in the field, and collect our samples, et cetera, et cetera. This is a complement technology for what we do.
Yes.
It's much, using that type of data or techniques is much more limited in Ontario. There's a lot of forest cover and overboard, correct?
Yeah, well, that's why I showed that example of using the geochemistry and the magnetics and the gamma ray spectrometer, because that wasn't good trained for. I looked at the remotely sensed data, and there was just too much forest cover. Now you can even in forest cover areas. What I tend to do in the past is I used a ratio and try to highlight the bedrock, like a 2/1 ratio, for example, will highlight bedrock. So what I try to do is just highlight all the bedrock on the image, and then just process that using a masking technique where you just process the outcrop. I've seen that done. Ben Rivard, my colleague in the University of Alberta, did a really good study of the Abitibi camp, and that's the approach he used. And he had hyperspectral data that could.
And what about maybe would the data be different during different seasons, like fall, spring?
Oh, absolutely, yeah.
Use that as a maybe. Yeah,
well, when there's snow on the ground, it's going to affect all techniques. Probably magnetics the least, but remotely sensed. If there's snow on the ground, that's all you see. And gamma ray, remember, gamma ray is not a penetrating technique like magnetics, right? It's from the first few centimeters the emission comes from, and it tails off exponentially with increase in height. So that's why when you collect gamma ray data, you have to fly pretty low to get a good signal to noise ratio.
Could you use those different signal limitations as a tool to somehow interpret what might be?
Yeah, well, for example, I've used winter imagery because of the low sun angle before, and the sun actually highlights some of the structure. So that type of seasonal imagery is really good. We conducted a study, which I haven't shown you today, that looks at multi-seasons for capturing superficial materials. And you can see how superficial materials can change over seasons. So we got May, June, July, August, and September imagery, and tried to put that into the package to see what evidence maps were giving us the best answers. So yeah, I mean, there's lots of stuff you can do with this. You can experiment, and lots of people are doing it now, including Metal Earth. So yeah.
Go ahead.
Have you worked on uranium explosion?
No, I've not done uranium. I've only used gamma ray data to map granitoid rocks in Nova Scotia and Laguna Train and New Elton. Yeah.
So most of this spectral imagery and gamma ray spectrometry, they'll be used in uranium.
Yeah. Oh, uranium. That's what the specialty is. Uranium, and also they use it for radon. In urban areas where they're escaping radon, they can sense that. And they've done studies using the gamma ray spectrum for radon. Yeah. All of these things. Yeah. Yeah. Like everything you see, I either got from Quebec, Ontario, GSC, and then there's for the remote sensing data, there's a website, USGS. you can download and search for images for free. Yeah.
Could you flip forward when you were in the Rae Province section? You had a slide that compared like the number of training points and the number of validation points, I think.
Okay.
The blue and the green ones, right?
Yeah.
Here?
Forward it was a table. Maybe one
Is that it?
maybe one more.
That one?
Yeah, okay. So it's an issue that like we encounter a lot in geoscience and the natural sciences as a whole, is when you're trying to do statistics, you have an inherently unbalanced statistical design because natural systems don't care if they're balanced or not. And if you look at like amphibolite, you only have 16 training pixels versus the granodiorite gneisses where you have 323. And so how does that affect the relative uncertainty and how do you mitigate that?
Yeah, so the general rule for that is take 2 to the nth. Nth is the number of evidence maps you have.
Okay.
And that number should be the minimum. In some cases, that's all we have. So the idea is how can we generate more points? Can we generate points around, you know, each lithological unit, or can we do our cross-validation on each lithological unit? So it's really how you prepare the data, and it's up to you how many. But that to the nth rule is probably pretty safe to go by when you're collecting your own training areas.
Right, and so that mitigates like the internal error.
Yeah.
I have a question about that data set. Each of those points there was a geochemical sample, right?
Yes.
And I think one of the, and you say it's
Oh,
always
wait a minute. They're based on field stations. We went to our database, yeah.
okay.
So the idea here is we had a strong database of lake sediments. We had a strong base of stations. So is that cheating? Well, no, because you could go out and field, as I said, and take your first year database that you've done and produce something like this, all right? And see how that fits the data. So you can build your map on the fly. The next season you go out, you're only going to make a better map because you've got more field follow-up to work on. So that's my opinion anyway. So, does that answer the question?
Yeah, sort of the question was really, if you, I mean, that's a lot of, someone's gone to a lot of sites then, put a lot of effort into that. I guess the question is, you say you have to go and validate stuff in the field, but if you collect all your remotely sensed data and use that, can you decrease the number of places you have to go to in the field?
What I use in this environment, what I would use is the Landsat data and try to isolate outcrop. That's what I generally use, the Landsat, except in Victoria Island where you could see the rocks are expressed from a spectral point of view. So, yeah, so it's tricky. There's a lot of issues I've skipped over in doing all this that are very important. And in the literature, you can see tons of information like how do you best select non-mineralized sites? Is it random, or is it low potential zones, or how do we do that? And so there's lots of papers on looking at that. So there's lots of issues. Yeah.
Well, I know in this area specifically, there's a lot of like structural stuff going on. So how do you take that into effect? Because like I know on the western side of the map, we're pretty close to the Stover tectonic zone.
Yeah. Well, this had nothing to do with structure. This was just trying to predict the lithological units.
So if you were on a structure running through the middle, would you not be like have different signatures on one side versus the other?
Yeah, you could, but as long as you sampled those, right? Produce a training area set of those samples, you'll do all right. For structure, I usually rely on the magnetics, vertical gradient, tilt, et cetera, because you can see. I'm involved in studying faults now across the Superior, and we've used. I interpret the magnetic data because it's wonderful data to interpret. But don't forget about gamma ray spectrometer too. In the right area, it can work fairly well.
Yeah, Sarah, we'll make this the last question.
If you could go a few slides forward where you were ranking, I think, different
Yeah.
techniques. Yeah, right, this one.
Yeah.
So on the first column is the rank of different
Yes.
sources of information.
Yeah.
So
And this is the sensor, and this is the actual band.
right, I see like a lot of spectral data have higher ranking, but total field magnetics has a rank of 20. So I'm a bit worried.
It contributes, but look at the difference. Hold on.
So is it? Are you saying that?
There. Look at the difference between the mag, just visually, what you can see, and what you can see on the gamma ray data. Like the mag is fantastic data, but the point I'm trying to make is it depends on the geologic environment. So if you look at that, that's a pretty good gamma ray image, in my point of view. Is that what your question is?
So there is a context to that ranking in the sense that interpret bedrock geology, like the composition.
Yeah.
It may be case dependent on where the
Yes.
data is coming from.
Yes. Yes.
If you're trying to, which you just said a bit earlier, derive structural information from it.
Yeah.
MAG data set is very, very useful. So it's
Yeah. Yeah.
It's
Yeah.
There is a context to that ranking.
Yeah.
It doesn't.
I'm just giving you some basic ideas to whet your appetite. I don't know whether you guys get a lot of statistics here or you get any remote sensing. I know you get geophysics expertly through Richard, but is there any statistics you guys have to take, or machine learning, or any of this kind of stuff taught here? No, because this is the GSC, believe it or not. Now, if you want jobs at the GSC when you get up, everything is AI now, artificial intelligence. The new deputy minister came in and had a hankering that we should be looking at AI. So the metals program now at the GSC is not even mapping, not field mapping. It's harvesting data from all the various databases and data sets you have to do this kind of thing. So do I agree with it? I would never say this technology replaces field mapping. How could it? But you see some things in this technology that are harder to see on the ground. So that's why I'm saying it's a mix of both technologies that we should be harnessing as young geologists coming up the ranks.
Okay, good. Well, thanks very much. We'll draw a close there. So thanks very much.
Thank you. Thank you so much.